Okay, write the proof of limit an as n tends to infinity is equal to 0 if an is equal to 1 over n, where n is a natural number. This an is a function from natural numbers to real numbers. Prove हे आपण लिहिलेलं आहे, परत एकदा तुम्ही लिहू शकता का, जस्ट चेक करता. Prove that limit 1 upon n as n tends to infinity it is equal to 0. Okay, so the proof of this is epsilon is greater than 1, which is given to us. You have to find out capital N such that for every capital N greater than, for every number a small n greater than capital N, you have 1 upon n minus 0 less than epsilon, and these are the simple calculations. If we take it epsilon is equal to 0.01, we get capital N should be greater than 100. So if we take n is equal to 101, we get the desired limit less than epsilon. Okay, so if we have all the definitions of the limits with us, and if we remember them, we can appropriately use them to prove the desired result. Okay, let me check with you second. Limit n tends to infinity an is equal to if an is equal to n, what will be the limit and y will be the limit? Find and prove. This will be plus infinity, right? The limit will be plus infinity. Write down the proof of this. Okay. Let m greater than 0 be given. Choose n greater than m. Then for every n greater than m, what we have? For every n greater than m, we have a n which is equal to n greater than m. Okay, how do we do these calculations? I mean, that is what are the those are the calculations, nothing else. You have been given n and you should show that you get n which is bigger than m. This implies limit n tends to infinity an is equal to plus n. So basically you need to find out the number n, capital N, beyond which if you take any number you will achieve the desired limit. That means you will achieve the value of your function greater than m. So now this is little more theoretical. So let me give you a numerical where you are supposed to prove limit, and you will get a clear idea. Limit n tends to infinity 3 raised to 2n minus 1. How much is this limit? N to infinity. 3 to the power 2n minus 1. Of course, this limit is going to be plus infinity. Prove that is plus infinity. You need to find out value of n beyond which any value of natural number if you take, you will stay greater than the given number. So proof will go like this. Let capital N greater than 0 be given. Now rough work we have to do. What we want basically is value of M is, you give me a number, I give you a number greater than that. Okay, so 3n, 3 raised to 2n minus 1 should be greater than m. We need to find out what is the value of n. Now 3 is greater than 1, therefore taking log of both sides, we won't affect the inequality. So log of 3 raised to 2n minus 1 is 2n minus 1 log 3 should be greater than log m. Correct? Now log 3 is greater than 0, therefore 2n minus 1 should be greater than log m upon log 3. n should be greater than log m upon log 3 plus 1, and therefore n should be greater than half log m upon log 3 plus 1. So choose n greater than half log m upon log 3 plus 1, and then do reverse calculations and show that this happens. I mean, you have to write down all these steps in opposite direction and show that this happens. Therefore, by definition.
तर पण हीच व्हॅल्यू का आपल्याला माहिती आहे की 3 raised to 2n minus 1 हे इन्क्रीजिंग फंक्शन आहे. कुठल्या व्हॅल्यू साठी इन्क्रीज होणार? 3 raised to 2n minus 1 इन्क्रीजिंग फंक्शन आहे ना, म्हणजे कुठल्याही व्हॅल्यू नंतर ते इन्क्रीजच होत राहणार आहे. मग हीच व्हॅल्यू का घेतली?
कुठली घेतली व्हॅल्यू?
n greater than half log m by log 3.
ती एकच व्हॅल्यू कुठे आहे? m वर डिपेंडंट आहे. तू m दे, मी व्हॅल्यू सांगतो. मी आता घेतलेली कुठची?
कुठल्या पण m साठी इन्फायनाइट व्हॅल्यू असणार की ते इन्क्रीजिंग फंक्शन आहे, म्हणजे इन्क्रीजच होणार ना.
अरे राजा, इन्क्रीजिंग आहे हे आपण नुसतं ग्राफ कडे बघून म्हणतोय. ते इन्क्रीजिंग फंक्शन आहे हेच प्रूफ आपण आता लिहितोय. तू इन्क्रीजिंग फंक्शन आहे तुला प्रूव्ह करायला सांगितलं तर कसं करणार आहेस? ग्राफ काढून ना. हा, तर ते तुझे म्हणतोयस इन्क्रीजिंग फंक्शन आहे ते प्रूफ लिहून झाल्यावर म्हणायचं की ते इन्क्रीजिंग फंक्शन आहे. Okay. Let me just give you one more so that you practice. Prove that limit n tends to infinity 1 minus 2n is equal to minus infinity. Given, let capital M greater than 0 be given. What we need to show is 1 minus 2n is less than opposite of n. Correct? So 2n minus 1 is greater than m. 2n is greater than m plus 1. n is greater than 1 upon 2 times m plus 1. Choose n greater than 1/2 m plus 1. implies 2n greater than m plus 1, implies 2n minus 1 greater than equal to m, implies 1 minus 2n is less than minus m, hence proof. Okay, this is what is the method of doing it. Now I give you something which is going to make you think. Limit n tends to infinity, a raised to 1 upon n is equal. Find with proof. Limit n tends to infinity, a raised to 1 upon n. N is a natural number. A raised to 1 upon n. This limit, answer for this limit is going to be 1, but there will be 3 cases. Because when you are dealing with a raised to x function, I mean we need to separate this function in 3 parts. If a is 1, a between 0 to 1, case 2 a is equal to 1, case 3 a greater than 1. These are the 3 parts, and that is how this function is going to be a little different. Okay, so maybe we have to write proofs, 3 different proofs for 3 different cases. Think about it. I mean, if a is equal to 1, then it is easy. Case 2 is easy. Of doing it, what you are writing is more or less correct. Let me show you one more method of doing it. Now let me take case a greater than 1, case 3, a is greater than 1. Now therefore a raised to 1 by n is also going to be greater than 1. If a is greater than 1, then a raised to 1 by n is also greater than 1 for every n belonging to natural number, right? So now let us convert this into equality. A raised to 1 upon n is equal to 1 plus some small number h, and let me prefix n to it because that h will depend on what n you take. So converting inequality into equality. This gives us a is equal to 1 plus hn raised to n, where n is a natural number, and therefore here I can write that 1 plus hn raised to n is going to be greater than 1 plus n times hn by binomial theorem. This is binomial expansion, and I am taking only first 2 terms and ignoring the rest. Therefore RHS is going to be less than this quantity, correct? So a is going to be greater than 1 plus nh. Therefore h n is equal to hn is equal to a minus 1 upon n. Is that okay? So I am just considering this equality and writing hn is equal to a minus 1 upon n, and now you observe that a is greater than 1, therefore this numerator is positive and n is tending to, so limit n tends to infinity hn. What will happen to hn? it will be a minus 1 upon n, which is limit a minus 1 n tends to infinity into limit 1 upon n tends to infinity. This is equal to uh, a minus 1, whatever this constant is as n tends to infinity, and this is going to be 0. Therefore, answer is going to be 0. So, Hn will tend to 0 as n tends to infinity. Therefore, this implies limit n tends to infinity a raised to 1 upon n, which is 1 plus Hn, will tend to. बघा समजते का? Now, you have converted inequality into equality and then found out the limit of the small increment, and that increment tends to 0. That is what we have proved here. I mean, whatever proofs you have written were not wrong, but this is getting into the bottom of the calculations and finding out what is this limit. Okay, now let me write down the proof for case 2. There is a small difference but similar treatment. Case 2, a is between 0 to 1. Okay, so if a is between 0 to 1, then a raised to 1 upon n is going to be less than 1. Correct? So here the adjustment that we are doing is a raised to 1 by n, let a raised to 1 by n is equal to 1 upon 1 plus hn. In the denominator you are adding something, small fraction, so that this total fraction becomes less than 1. Now therefore a is equal to 1 upon 1 plus hn raised to n, which is now going to be less than or equal to 1 upon 1 plus n times hn. Okay, therefore a so a is less than or equal to 1 upon 1 plus nh. So if we simplify, we will get hn is less than 1 upon n inside bracket 1 upon n minus 1. Now if we take limit hn as n tends to infinity, hn is again going to be, because this is another constant, this is again 1 upon n, therefore this will be equal to 0, and hence again we will prove if a is less than 1 and greater than 0, still we get limit n tends to infinity a raised to 1 upon n is equal to 1. Okay, and case 1 was constant, limit n tends to infinity a raised to 1 upon n is equal to 1 if a is equal to 1, because 1 raised to any number is going to be equal to 1. So considering all three cases, we have finally limit as n tends to infinity a raised to 1 upon n tends to 1. This is very, very important. So does not matter whether a is less than 1 or greater than 1 or equal to 1, as n tends to infinity a raised to 1 upon n will tend to 1. So this is what is convergent. I mean, we defined so this is convergent limit. Okay, now let me give you one example where you will struggle to get me the limit. Check whether you can give me the limit in this case. Find limit an as n tends to infinity, where an is equal to n plus minus 1 raised to n times n, minus 1 raised to n times n. Find this limit. Limit n tends to infinity 1 plus 1 upon n raised to n. Now, behavior of 1 upon n as n tends to infinity we have observed. Behavior of a raised to n we have observed. Now, this is the limit which is very interesting because this is not 1 raised to n. This is 1 plus something raised to n, and 1 plus small quantity raised to big quantity. That makes it interesting. So try to find out. Maybe you are aware of this answer, but how can we imagine this and try to prove what should be the limit of this? Is it convergent? Is it divergent? Is it oscillating? And if it is convergent, what should be the limit? How much it will be, etc. We are required to figure out. So I'm giving you some time to find out this limit on your own, and if internet helps us, we will write down the proof of this end of the lecture today. But if it gets discontinued, I mean, how many times in one lecture internet is giving me problem? Let us see how can we go about it. So I am right now giving you sufficient time to think about it. Let us do a theorem. Let A and B a real valued sequence. 1. Let A n be not decreasing. Sequence. 2. Let A and B bounded above. Then 3. N is convergent. Try to write down proof of this theorem first, then we will use this theorem to show what happens to this limit. So if we want to prove this theorem, what do we need to prove? Claim limit n tends to infinity an is equal to, it is convergent, so it should be convergent to some value L. That is to be proved. An will get converged to some value L. This is what is to be proved because it is a non-decreasing sequence and it is bounded above. So in that case it will converge to, as it tends to infinity, it will converge to some value. This is what is required to be proved. So shall I write the proof or wait for some time? आज तुकडे तुकडे झाले सगळे रेकॉर्डिंगचे. Okay, so if we want to claim limit n tends to infinity as L, we start with statement number 2, which says sequence an is bounded above implies an as a LUB. Let capital N be LUB of sequence an. Let epsilon greater than 0 be given. By gap lemma, there exists k belonging to natural number n such that m minus epsilon is less than ak is less than equal to m. This is already proved. Okay. Now let n be greater than k. This implies an is greater than equal to ak. This implies m minus epsilon is less than ak is less than or equal to an is less than or equal to m. This implies m minus epsilon is less than an is less than m plus epsilon. Therefore, by definition, limit n tends to infinity, an is equal to m. Theorem proved. Tell me if you have any difficulty in this. So by gap lemma, you have found out one element between the gap m and m minus epsilon. And then because it is non-decreasing sequence, you could find out another element of that sequence which is greater than or equal to ak, which is also there between m and m minus epsilon, and therefore an for every n greater than k is going to be between m plus epsilon and m minus epsilon. That is what we wanted to prove when we said limit n tends to infinity, an is equal to n. So this is what is very important. It is a non-decreasing sequence and is bounded above, therefore it is convergent. That is what is the result that we are getting out of this, and this result is going to be very useful in doing this particular problem. So we expect this limit also to be convergent. Let us say L, and we will try to estimate what is the value of this L. So if we want to show that this sequence 1 plus 1 upon n raised to n is convergent to L, what we need to show is the prerequisite conditions of this theorem. So to show that 1 plus 1 upon n raised to n is not decreasing and is bounded above. This is the sequence an which is non-decreasing and is bounded above. If we could prove this, then by this theorem we can say that it is convergent, and we will find out what value it converges to. So now the solving this limit is solving or proving these two statements. 1 plus 1 upon n raised to n is non-decreasing and is bounded above. So I give you time to do this, and then I will write down the proof of this. showing that it is non-decreasing sequence, what we need to do is to show that an is less than or equal to an plus 1. Now an is 1 plus 1 upon n raised to n is less than or equal to 1 plus 1 upon n plus 1 raised to n. If you remember, when we studied inequalities, in problem number 7, point 1, I had told you at that time that this inequality is important because we will require it in calculus. Okay, so we had done it at that time, maybe by two methods. We can do it by two methods. One, your regular Amgm inequality, and two, binomial theorem. So now I am not giving you time to do that. Let me explain you both of them. How will Amgm inequality? This is n plus 1, by the way. Sorry. How will Amgm inequality will prove this very quickly? We have to consider it as 1 plus 1 upon n raised to n into 1 raised to 1 upon n plus 1. This is geometric mean of n plus 1 object is going to be less than or equal to 1 plus 1 upon n plus 1 plus 1 upon n. How many times? N times. N times. Plus 1 divided by n plus 1. Okay, so 1 plus 1 upon n times, that is n into 1 plus 1 upon n plus 1 upon n plus 1, which is equal to n plus 1 plus 1, that is n plus 2 upon n plus 1, which is equal to 1 plus 1 over n plus 1, which is RHS. So this is very fast way of doing, because you are using strong tool which is Amgm inequality, and therefore you get LHS is less than or equal to RHS. That is method number 1. Method number 2. One plus 1 over n bracket raised to n. If I write binomial expansion of this, it is 1 plus n times 1 upon n plus n into n minus 1 upon 2 factorial times 1 upon n square plus n into n minus 1 into n minus 2 upon 3 factorial into 1 upon n cube plus so on. Now let us trim this. This is 1 plus 1 plus. Now if I distribute this n square to each one of them bracket, I get 1 into n minus 1 upon n into 1 upon 2 factorial plus n minus 1 upon n into n minus 2 upon n into 1 upon 3 factorial, and so on. I can always keep doing this. Okay, so one thing is for sure, that this quantity is going to be definitely greater than 2, because this is 1 plus 1 is already there and all these terms are going to be positive. So this is what is expansion. But then now let us see what we can do, let us write down 1 plus 1 upon n plus 1 bracket raised to n plus 1. First term is 1 plus n plus 1 times 1 upon n plus 1, that is second term, plus n plus 1 into n upon 2 factorial into 1 upon n plus 1 raised to 2 plus n plus 1 n into n minus 1 upon 3 factorial into 1 upon n plus 1 raised to 3 plus dot dot. Okay, if we simplify this further, we get 1 plus 1. So 2 is already there. 1 plus 1 plus, now let us distribute 1 bracket to each. First one is 1, second is n upon n plus 1 into n upon 2 factorial plus n upon n plus 1 into n minus 1 upon n plus 1 into 1 upon 3 factorial plus dot. So now compare term by term. See, this is positive, this is natural number, these quantities are also positive, this is positive, this is positive. So negative sign is not involved in anywhere in this expansion, right? So first term is same as first term, no problem. Second term is same as second term. Now let us compare these two terms. Multiplier is same, 1 upon 2 factor. Is this bigger or is this bigger? So we have to compare n minus 1 upon n and n upon n plus 1. N upon n plus 1. Can we compare these two and find out who is bigger, who is smaller? Okay, so we want to conclude with this. This is n square minus 1. That is n square. Everything is positive. So n square minus 1. This cross multiplication is of course going to be less than or equal to, or less, not equal to, strictly less than. This is equal. So term number 3 is less than this term number 3. Similarly, we can prove that term number 4 is going to be less than term number 4. So term by term, first expansion is less than, and there is one extra term in this because this is n plus 2 terms expansion. Total number of terms here, so in RHS we have total one term extra, and every corresponding term after second term is greater compared to LHS, and therefore LHS is less than or equal to RHS. Do you this term by term expansion? I give you sufficient time to write this, and then we will prove the second part of it. Pause. Now let us look at this part. N into n plus 1 upon n okay. So 1 plus 1 upon n raised to n, we said it is 1 plus 1 plus n plus 1 upon n times 1 upon 2 factorial. So n plus 1 upon n can be written as 1 plus n minus 1 upon n times 1 upon 2 factorial. Therefore it is 1 minus n times 2 factor 1 upon 2 factorial, plus next term is 1 is gone, so 1 minus 1 upon n into 1 minus 1 upon 2 upon n into 1 upon 3 factorial plus next term will be 1 minus 1 upon n into 1 minus 2 upon n into 1 minus 3 upon n into 1 upon 4 factorial and so on. Okay, so this is what is going to be the expansion of 1 plus 1 upon n raised to n, binomial expansion. So now we want to say that this sequence is bounded above. What are we trying to prove now? We are trying to prove that this is bounded above. Okay. So this sequence, now this is going to be, n is going to be a natural number, therefore this quantity will be definitely less than 1. Every bracket that is being written here is going to be less than 1. Is that right? And therefore if we consider all those brackets to be 1, then I have to write down this quantity is going to be less than, this quantity is going to be less than 1 plus 1 plus 1 upon 2 factorial plus 1 upon 3 factorial plus dot 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 plus 1 upon n factorial, and n tends to infinity. Is that correct? Each bracket is less than because each bracket is less than 1. So suppose if I assume each bracket to be equal to 1, I get this. Okay. Now let us look at this. 1 plus 2 factorial is, this is equal to 1 plus 1 upon 1 into 2 plus 1 upon 1 into 2 into 3 plus 1 upon 1 into 2 into 3 into 4 plus dot dot. Okay. So now increasing numerator is decreasing the fraction. Is that correct? Increasing the numerator is decreasing the factor, or decreasing the numerator is increasing the factor. So I can write this is going to be less than, equality is gone. So it's going to be less than 1 plus 1 upon 2 as it is, I write plus 1 upon 2 into 2. So instead of this 3 here, I wrote 2. That means I have decreased denominator. That means I have increased fraction. This was 1 upon 6. This is 1 upon 4. So this is bigger than this. So that inequality I am maintaining here. Similarly, the next one, 3 into 4. What I do is I write 2 for all. 1 upon 2 into 2 into 2. I replace 3 by 2 and 4 by 2 also. So I get 2 raised to 2 raised to. So this is 2 raised equivalent to 2 raised to 3 plus 1 upon 2 raised to 4 plus 1 upon 2 raised to 5 plus dot dot dot. Do you realize the estimation or dealing with inequality? So now this is easy for me to calculate, and therefore I have done it like that. And now therefore it is equal to, what is this? This is geometric progression. 1 plus 1 plus 1 raised to 2 raised to 1 plus 1 raised to 2 raised to 2 plus 1 raised to 2 raised to 3 plus dot dot dot. Correct? So this is geometric progression, and therefore this is going to be equal to, so if we start from here, then first term is 1 plus first term is 1. Total number of turns, I mean common ratio is half. So a upon 1 minus half. That is the answer for this geometric progression, which is equal to 1 plus 2, which is equal to 3. Oh, this quantity will never exceed 3, and it will be never less than 2. So what we can conclude out of this is 1 plus 1 over n, as I intended. Now it should have been limit E is going to be less than 3. So it is bounded
तर
above.
तिथे हे पाहिजे लेस दॅन इक्वल टू पाहिजे
Okay.
तर 2 आणि लिमिट म्हणजे ग्रेटर दॅन इक्वल सर n इक्वल टू 1 टाकला की 2 येतो
इथे म्हणतोस का? हा. Okay. So it is bounded above and is non-decreasing sequence. Hence, limit n tends to infinity 1 plus 1 upon n is equal to L. Now this L, the new name which we are giving to this L is your new invariant, the last invariant in mathematics which you are not aware of is E. This is the value of E. So E is somebody which is an irrational number between 2 to 3. That is where this limit is going to go and converge. Write down this. That is where we are going to stop today and we will see applications of this next lecture.